Now begins a second video dealing with stoichiometry problems where we're given more complex information to start with. And if you remember from the first video, the key to this is once we get down all of our givens, can any number and unit given be expressed as a conversion factor? So we are going to continue with the Stoichiometry Practice 2 worksheet, problems 8 and 9, and learn what we can learn from those. And so we're going to start with problem 8. So if you could pause and go ahead and read that, and then we'll begin solving. Okay, so first, very, very familiar that we don't quite know what coke is. You know, our region, southwestern Pennsylvania, has its historical roots in steel and, of course, steel industry and coal mining. Coal is converted into a product that is called coke that is then utilized by steel mills in the process of creating steel. All right, so coke, it is just the name that's given to this material that is 85.5% carbon. Okay, the question is, how many metric tons? Okay, well first, what is a metric ton? We're going to learn a lot through these problems. So I would never ask you to problem solve with these without us having walked through a couple of these together and learn little things like these. 1 metric ton is 1,000 kilograms. All right, so how many metric tons of carbon dioxide can be produced? Okay, so in our chemical reaction, we're going to be making CO2, How many metric tons of CO2 can be produced from the combustion of 4,700 kilograms of coke? Okay, 4,700 kilograms of coke, that is 85.5% carbon. Okay, again, we're getting that combustion. Well, we know combustion is burning, and we usually have a fuel that is then being reacted with oxygen. Okay, so the coke is providing the carbon that is then reacted with oxygen to produce carbon dioxide. So really our formula, our chemical equation, is carbon plus oxygen yielding CO2. And we're balanced as written. Okay, so the coke, and we're starting with this amount of it, provides the carbon for the reaction. And we're ultimately looking for the metric tons of carbon dioxide that are produced. So we have this given, I'll go ahead and outline it in blue, and we have this given. All right, a key absolutely is asking, can we express any of these as a conversion factor? And we've seen that percentages can be expressed as ratios per 100. Sorry, I didn't mean to pause that. And so we can rewrite this to mean that there's 85.5 grams of carbon in every 100 grams of coke. All right, so this became that given. So I really have this and this, a mass and then a conversion factor. I'm going to go ahead and begin with my more straightforward given, the mass. All right, so it's 4,700. Oh, and there is a decimal there. So I know I have 4 sig figs in this. 4,700 kilograms of Coke. And if you want to put that over 1, I tell you, I see right above, I have an expression per grams of Coke. So the first thing I'm going to do, let's get out of kilograms. And we know 1 kilogram is 1,000 grams. And next, every 100 grams of Coke is 85.5 grams of carbon. Okay, now we can get into our chemical reaction. And there's 12.01 grams of carbon in every 1 mole of carbon. Ah, nice. And per our reaction, every 1 mole of carbon, okay, remember I'm looking for this. So see, I'm getting closer and closer and closer, is 1 mole of CO2. Okay, now we need metric tons. Okay, so metric tons are in terms of kilograms. So I'm going to need to get from moles to kilograms of carbon dioxide. And every 1 mole of CO2 is 44.01. And that'll leave me in grams. And I know every 1,000 grams will be 1 kilogram. And every 1,000 kilograms is 1 metric ton of CO2. Whew, what a problem. This is, wow, very, very impressive. Very impressive. Okay, so we carefully begin. Oh, I have to zoom out so that we can fully see all of it. But let's see, this has 4 sig figs, but 3, so I'm limited to 3. And when I do all of my math very carefully, we get 14.7 metric tons. 14.7 metric tons of carbon dioxide. Whew, very impressive, very impressive. 14.7, let me focus it to make sure it's nice and crisp for you. 14.7. Okay, so let's look at number 9 and see what we can learn from that. Okay, so if you want to go ahead and pause it and read, and then we'll begin problem solving. Okay. How many milliliters of a 25% sodium hydroxide solution will be needed to completely react with 15.8 grams of sulfuric acid? All right, and I am also told the density, get that a little darker. That's too dark and then see shadows, but let me get a little closer now. All right, sorry, nice and crisp for you. Sorry about the pause, sorry. Oh, we need to focus that again. There we go, there we go. All right, and we're told the density of the sodium hydroxide solution. So just to avoid making any errors, I'm going to make sure I write, the density of this solution is 1.10 gram per milliliter. All right, first chemical equation. So I think it's pretty clear. We're going to be reacting sodium hydroxide, and you can definitely tell it's dissolved, and I venture to say it's safe to say water, with sulfuric acid. We don't know yet, but for this to be an acid, it would have to be an aqueous solution. That's okay. We know phase symbols are not required at this point in time. Double replacement, so this will be sodium sulfate, and we would need a 2 plus 2 HOH or H2Os and we need a 2 there to balance. All right, so this is quite a real world example. We want to know the volume of a 25% sodium hydroxide solution. So the solution, if we can imagine, we have a bottle that I bet, would read 25% NaOH. Okay, so the solution is the mixture. And the 25% is the part that sodium hydroxide is in the mixture. So just as we've been doing, we can express percentages as mass ratios. So we have 25 grams of NaOH for every 100 grams of the solution. And the density. Now, what this means, right? This is how many grams of solution I have per milliliter. That can be directly interpreted as a conversion factor as well. We can say it will be a mass of 1.10 grams of solution, because it's density of solution, for every 1 milliliter of solution. So when I measure this out, if I would measure 1 milliliter, it would mass 1.10 grams. This is of the mixture, not just the NaOH with the water. And we know that we are reacting it with 15.8 grams of H2SO4. All right. We needed our full balance equation to know the mole relationship between these. Here in this problem, I am just worried about what volume I need to react all of this away. So I'm just focusing from reactant to reactant. We have three givens. The mass of the H2SO4, a mass ratio of NaOH to grams of solution, and then the density of the solution. I know I want to answer about the NaOH. So because I want my answer to be about the NaOH, that encourages me to start with this, but also it's the simpler given. So let's dig in. Let's let the problem really guide us step by step. So if we start with 15.8 grams of H2SO4, you may put that over 1 if you would like. Then we get the formula mass of 2 hydrogens, 1 sulfur, and 4 oxygen. That is 98.03 grams in every 1 mole. All right, we get to moles, so we can do the mole ratio. Every 1 mole of H2SO4 can react with 2 moles of NaOH. All right, now we're in terms of the NaOH. But I ultimately want to know milliliters of the solution. This is mole of NaOH. And if I look, here is gram of NaOH. So let's get this to grams. 1 mole of NaOH is 40.01 grams. All right, then let the givens help you. I don't want grams of NaOH. I ultimately want milliliters of solution. So look, okay, to cancel grams of NaOH, I would need that in the denominator. This is my relationship, and I know I can flip this if needed. And I was told I have 25 grams of NaOH for every 100 grams of my solution. That cancels grams of NaOH. I'm getting closer. Now it's grams of solution. Okay, but question was for milliliters. Well, look here. Being given the density, you need grams of solution to cancel. And we were told there's 1.10 grams for every 1 milliliter. Dun, dun, dun. Look at that. Look at that. So we laid it all out, taking a step at a time, really, letting the problem guide us with what unit we needed to cancel and utilizing our givens whenever they made sense. And what we'll get from here, 3 sig figs, 3 sig figs, 3 sig figs is 46.9 milliliters of the NaOH solution. Okay, so we saw where we were given solution information, but you guys are such strong problem solvers. So just trust yourself. You know how to do dimensional analysis. You know the steps of stoichiometry. Trust yourself and move forward with confidence with these problems.